So when I say teach, how to think brilliantly, creatively in mathematics, what I mean is all the things that basically people in the math community, math teachers, math professors, math doers, math thinkers, math lovers strive for every day. Basically this sort of thing. I want to just competent, joyous math doing. Let it be joyous. Let me do it freely. See the big picture, make the connections, just cut through the clutter. The school curriculum is full of so much clutter, jargon and words. Just cut through all that, just get to the ideas. Set the stage for insights, lots of mulling. Okay, I will admit, I was a very strange high school teacher. Often my classes would get stuck in a problem. And my homework that night for those kids was this, and I literally meant it. I would like you to go for a 20-minute walk, and I mean it, go for a 20-minute walk and not think about this problem. Because next day, someone will invariably come back with a flash of insight that will move the conversation forward. And that's what mathematicians do. When you're stuck, just let it go and go for a walk or something, or go do something else. And so you've got to let your subconscious work on stuff. Let's teach kids that. Actually teach kids that. So, lots of mulling. Use patience and perseverance just to nut things out. I realize actually, nut things out, I think this is strange. Do you know what I mean by nut things out?
Yes.
Or just, just try things, just think things through. Yeah, okay, this is Ollie, sorry. Develop intellectual agility, and I don't mean speed. People equate being able to do lots of equations and computations in your head fast as being math joy. Ask me to do a multiplication problem in my head, will not be fast, I tell you. I'm not good at computations. Move beyond the what questions, ask for the whys and the what else and the what ifs. What if is such a rare question in the school world? I'd love to just change the rules and wonder what else happens. That's the fun stuff. And just engage in joy, just enjoy the intellectual play, innovate and try things. Flail and get things wrong. That's what life is like. You always get things wrong all the time. But you have to get things wrong so you know what's right when it happens. My real point is that all this is just great skills for all subjects. It's actually, I would say they're actually life skills. I want to teach my kids life skills. So, since I had this brilliant, modest title about brilliant creative thinking, so here are my 5 principles out of my head that I'm going to basically address tonight. So here's what I think mathematicians do, what I would advise the world. Visualize the power of a picture. It's really strong, it's really strong. In fact, that was my biggest culture shock leaving the university world to become a high school teacher. How much drawing a picture is eschewed from the high school curriculum. For some reason it seemed like drawing pictures is meant to be like too young or something like that. I think something changes. I know in middle school, kids encouraged to draw pictures in math.
We're beginning to do that now.
So it's only new, which is strange because to me that's what mathematicians do all the time. Think of a picture, draw a picture. I'll explain these things as I go along. Use common sense. I mean that sounds like a silly thing to say, but mathematicians work very hard to avoid hard work. Like, think hard about how to avoid hard work. It's a more life skill. Playing, I talked about playing tonight. Let understanding be the way to go rather than memorizing. In fact, understanding is so much easier than memorizing. Memorizing is hard. That's hard work. Good for any kid who can memorize all the stuff. That's something, but it wasn't fun. And then, be very clear what you don't know. In fact, don't be shy of what you don't know. In fact, walk into the hazy thinking. When you realize something's not quite right, actually walk into it rather than run away from it. Be very clear what you don't know. Oh, so this is the structure I'm going to do talk tonight. Those 5 things. So here goes. What I mean by visualize, think of a picture. Here's actually my favorite example of all time of the beauty of a picture in mathematics. So what I've drawn here is a 5 by 5 grid of dots. 5 rows of 5 dots. That's 25 dots in total. But I'm going to claim this is actually a picture of the sum 1 plus 2 plus 3 plus 4 plus 5 plus 4 plus 3 plus 2 plus 1. Can you see that sum in that picture? Okay. Can you see 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, 4 dots, 3 dots, 2 dots, 1 dot in some very natural, beautiful way? Yeah, some people are saying put their hands in a funny slant here. Yeah, I did diagonals. 1 dot, 2 dots, 3 dots, 4 dots, 5 dots. My square's not very square, this projection. 4, 3, 2, 1. There it is. See it? 1 plus 2 plus 3 plus 4 plus 5 plus 4 plus 3 plus 2 plus 1. Okay, without doing the arithmetic at all, what must that sum equal? All 25 dots. Not a lick of arithmetic, and I know the sum. 1 plus 2 plus 3 plus 4 plus 5 plus 4 plus 3 plus 2 plus 1 has to be 25. All right, this is powerful. What's the sum of all the numbers up to 10 and back down again? 1 plus 2 plus 3 plus 4, 5, 6, 7, 8, 9, 10, plus 9 plus 8 plus 7, 3 plus 2 plus 1. What will that have to equal? 100. It must come from the diagonals of a 10 by 10 grid, 100 dots. What's the sum of all the numbers from 1 up to 1,000 and back down again? You've got half a second. 1 to 1,000 and back down again. Must be 1,000 times 1,000, which is a million. That's the hard part. It's a million. Can you imagine doing that with a calculator? 1 plus 2 plus 3 plus 4 plus 5. But it's a million, and you just know it. The power of a picture. The power of a picture. Unfortunately, that doesn't appear in the high school or middle school curriculum as far as I'm aware. Certainly not in my day. That doesn't appear in the high school curriculum today. So that's not mathematics. Except, when I was a high school teacher, I had to teach this weird formula. And this formula says, the sum of the numbers from 1 up to n must be given by that equation. So for example, if I did the sum of the numbers, say, 1 up to 5, 1 plus 2 plus 3 plus 4 plus 5, the answer apparently is 5 squared, 25, plus 5, makes 30, divided by 2, apparently is 15. Right? So I had to teach that formula, and I realized, oh, yes, I can teach the kids the power of a picture. Because we just did, right then, 1 plus 2 plus 3 plus 5 plus 4 plus 3 plus 2, and it's 5 squared. Then I say, okay, does that sum at least resemble anything to do with what I was meant to teach as a high school teacher? And you can see right there, 1 plus 2 plus 3 plus 4 plus 5 is what I was meant to teach my kids. So we started with that, and I asked my kids, can we use this formula in any way to get what we want? Because after all, we see what we want within it. So suddenly I'm doing a great piece of just, I don't know, problem solving with the kids. Because I don't want to redo the work. And the kids would realize and tell me, well, there's what we want, and that part is almost what we want. But it's missing something. What's it missing? 5. What a shame. Oh well, I guess it's a useless idea. Except, right at that moment, here's a lovely life lesson. There's something in life you want. I advise you, make it happen. If you want a 5 there, make it happen. And deal with the consequences. If you put a 5 there, you have to put a 5 on the other side as well to balance it. Is that right? So if something like you want, make it happen. I want a 5 on the left. Well, I'd better have a 5 on the right as well to counteract it. That's my consequence. And suddenly now I see, the sum of what I want and the sum again. So 2 copies of what I want is 5 squared plus 5. Therefore, 1 of what I want must be 5 squared plus 5 divided by 2. Wow. So that was it. Okay, I taught my kids that formula now, but actually it was, they don't memorize it. They say it's the diagonals of the square. Just messed around with. That's the sort of play I like to do to teach the kids. Right, to me, multiplications of geometry problems, really a picture problem. For example, 23 times 17. To me, that's really a picture of a rectangle. It's asking for the area of a 23 by 17 rectangle. And I have to say to myself, who in their right mind wants to work with the numbers 23 and 17? No one. So my advice is, don't. What's the natural thing to do with that rectangle to make your life easier?
Go make half it. Triangle. Create 2 triangles. Create a grid, square.
Yeah, I mean, these are all great ideas, don't get me wrong. What if I did this and made it much funny numbers, 20 and 3 and 10 and 7, chop into 4 pieces? Is it now easier to work out the area of that oh, actually, what's the area of that piece right there? 20 times 10, 200, 30, 140, 21, that's all doable. In fact, now I can see that the area of the rectangle must be those numbers added together. Much more friendly. In fact, this is what we do teach kids. I mean, I almost did it in my head. This is the traditional long algorithm. I think it has a name in the middle school curriculum or primary school curriculum, whatever it's called. But to me, it's really this expanded form. It's exactly the same as that rectangle, just without drawing the picture. I would say, if you're going to do all that, might as well just draw the picture and see what's going on. And then, by the way, that's not actually what we teach most kids. We actually end up teaching kids this thing, which is a very compact version of that. Did I do something strange? Okay. This comes from the 1700s when ink and paper was very precious and would use as little of as you can. But the thing is, in the 21st century, we can be a little more wasteful. It's okay to take the extra time and write out all the pieces. You don't have to be compact. In fact, I personally, in my brain, if you ask me to do long multiplication, I get this wrong, because in my mind, I'm still doing rectangles.
What you did on the analogy, that's exactly how we were taught as well.
Exactly, I was taught that first.
Yeah.
I never had that as a kid.
No.
No, exactly. It's just, here's the algorithm, you need to know the answer. Well, if you're going to teach that thinking in the 21st century and you need to know the answer, I advise you to go that route. Seriously, in the 21st century, you've got to wonder why do we teach that thinking. All right. So to me, multiplication is just a picture. But actually, this was very handy for me as a high school teacher because those grade 4 or grade 5 teachers actually do my work for me as a high school teacher because in high school, we have to do the same thing, not in just base 10, 20 and 3, 10 and 7. We have to do these things called polynomials, 2x and 3x plus 7. It's exactly the same work. To multiply 2x plus 3 times x plus 7, just look at the pieces of the rectangle, add up the pieces, and go done. There's no need to do this thing. Oh yeah, oh actually, the diagonals are nice here actually. You've got 2x squared, you've got 17x, or the diagonal at 21. So actually the answer can be seen in the diagonals too, which is kind of cute. The lovely thing here is you can go backwards. So I gave you 2x plus 3 times x plus 7 and gave you this answer on the diagonals. What if I gave you the answer first on the diagonals and one side and asked what the top is? That is, I had to teach polynomial division as a high school teacher. Here's a lovely little fun game. You know these diagonals add up to these answers. Can you tell what that square must be then? It must be that diagonal. 2x cubed. So now's a little game. You know something times 2x makes 2x cubed. So the thing at the top better be x squared. Is that right? X squared times 2x? Yeah. Maybe we just keep filling in this grid. For example, do you know what this has to be now, this cell? Must be 3 times x squared, 3x cubed, 3x squared, sorry. But I know this table is going to add to 7x squared. Is that telling me anything?
3x squared minus, y minus 3x squared is equal to 7.
Something plus 3x squared makes 7x squared, so this must be
4x
4x squared? Perfect. Which means something times 2x makes 4x squared. See what the game I'm playing? It's just I'm just using my logic, I'm using my common sense. Except they get it wrong here, I put a typo in. I made the typo go away, there it is. You see the game I'm doing? 2x plus 3 must be 6x. Something plus 6x makes 2x, negative 4x, and off I go. Suddenly I'm just doing polynomial divisions because I'm just like playing a little Sudoku puzzle. That's the joy. What you do in grade 4 and 5, do it backwards, and you do high school now as well. Who doesn't love going on a roller coaster both forwards and backwards? It's kind of cool. All right, my point is we're all in this together. The storyline we put kids through from K through 6 to 7 through 9 through 12 is all one storyline. All us teachers are in it together. In fact, a very common student mistake in high school is that a plus b squared must be just a squared plus b squared. It seems very compelling and very natural thing to write. But the thing is, I said squared, I even used the word square. I used a geometry word there, square. So let's draw a square. There's an a plus b by a plus b squared. And now I can see that actually, yes, there was an a squared piece, yeah. There was a b squared piece, yeah. But there's extra stuff I missed, silly me. So the correct answer is actually a squared plus b squared plus 2 ab's. Bingo. So, you know, often kids are taught a word foil. Do you guys ever have the word foil? Are you still foiling in middle school? Okay. Well, I don't know what it means, like first, outer, inner, and last, or some mnemonics to figure out what to do. My point is, without even mnemonics, it's clear what to do if you just draw a picture. If you're talking about squares, then I advise draw a square. In fact, foil will let you down if they give you something like that. But can you see in your mind's eye the picture of that one would be square chopped up into 9 pieces? A plus B plus C on the top, A plus B on the C on the side makes 9 pieces. So you just have to chase your way and make sure you get all 9 pieces. Also, it's not quite square, there are 4 pieces by 3 pieces, must give you 12 chunks. Just make sure you get all 12. Draw a picture, just draw a picture, and follow your nose, all become clear.
So on the first one, you would have a square that would look like a rock for the 9 points?
Yep. And the second one you have, okay, it's not a square anymore, but same idea. I love the idea of just pushing ideas a little bit further with the kids. This is awesome. All right. So I really claim that a picture really leads to insight and deep understanding. The picture is so powerful. And by the way, there was one historical change that got people away from the visual. 2 plus 3 plus 4, that equals 9, I know. But there's actually a couple of ways to think of this. You could think of this as 2 plus 3 first, get 5, and then go add 4. Or maybe you think 2 plus 3 plus 4, 2 plus 7. So back in the medieval days, they had a symbol for how they want you to think through that problem. They used a horizontal bar called a vinculum. So this horizontal vinculum, so it meant, okay, if you draw a horizontal bar above the 2 and 3, it means group the 2 and 3 together first, do them first. So you get 5 plus 4 equals 9. Or for some reason you want me to think 3 plus 7 first, 3 plus 4 first, put a vinculum on top, say that's one group, and get 7, go 2 plus 7 is 9. So vinculum was very much used in the medieval period for grouping. It's actually a really great symbol because if things got really complicated, for example, something like that, can you see what to do nonetheless, despite how scary it is? Can you see what the first thing you meant to do?
Do 4.
You meant to do 4 plus 5, you meant to get 9. Then what are you meant to do?
9 minus 7.
So you can completely see what to do. That vinculum, just, I mean, that's absurd, I know. But even in that worst example, you still straightforward in what to do. But we don't do this anymore. We're in the 21st century, 7 centuries later, and we do that to kids. We do. Nested parentheses, is that right? Now, it's very hard for us adults because we've been trained how to think through that. But for a kid seeing this for the first time, that is very scary and not natural. So I see teachers do this. They say, okay, kids, don't be scared, take a deep breath, that's fine. Why don't you look for the innermost parentheses first and underline them? And then look for the next innermost parentheses, underline those. And then look for the next innermost parentheses and underline those. Do you see what's happening?
Vinculums.
We're going back to the vinculum. So it's interesting that the way we teach how to deal with this is to go back to the visual that was forgotten. So I have a question. What happened in the 1400s to make mathematicians go away from the vinculum? Why that changed from something that actually is very obvious and clear to something that's actually very hard to unravel? No idea? The printing press was invented in the 1400s. And the idea of the printing press was this great big wooden table, and they had little tiles, one for each symbol. So they'd lay out all the tiles of the words you want to write. Then you put ink on the tiles, get a great big piece of paper, put it down on the tiles, lift it back up, and there's your first page, and then rearrange the tiles, get the next page, and so on. But think about mathematics books. Trying to print the vinculum, which is like in between the lines, was a pain. So what they had to do was, first of all, arrange all the tiles without the vinculum, put it on the paper, lift it up, take all the tiles off, and then rearrange the vinculum tiles back in those half-line positions, exactly where they're meant to be, take the same sheet of paper, bring it back down, off we go. That is horrible, a pain. So they decided to go with a notation that keeps all the symbols in the same line. So when you're lining up the tiles on the printing press, it's actually easier to print. Here we are, as I said, 5 centuries later or something like that, still using the parentheses because of the printing press. Actually, on a computer, that's really easy for us to type now. And it's very easy to draw a page to it, it's actually kind of fun. The funny thing is, we still actually use the vinculum. Example. Do you know that little symbol? Do you know what that symbol means?
We call it a tick.
A tick. A check mark, tick. In mathematics, do you know what it means? Sorry? Radical square root. So this is actually a confusing expression because do you mean the square root of 9, which is 3, then add 7, or do you mean the square root of 9, the square root of 16, which is 4? So either you get 3 plus 7, which is 10, or you get square root of 16, which is 4. So what does that expression mean? Now the reason you hesitated on me that you didn't know what that symbol was, because we never draw the symbol alone.
There's always a line on top.
There's always a vinculum to go with it. We always draw the vinculum. We don't, that's called a radix, by the way, like radical radix. We're so used to drawing with a vinculum nowadays that we don't realize it's actually two symbols combined. So if I meant square root of 9 plus 7, I said, okay, I just want the 9 to be one little group. Then I'll take 3 plus 7 and get 10. Or if I really meant 9 plus 7 to be square rooted, I'll use the vinculum and say, I meant 9 plus 7, please. So we still use the vinculum right there. We use it so much we don't even realize it's two different symbols. We use it here. Do you remember the notation for repeated decimals? It means, please keep H2 as its own little group. In this case, a little group that gets repeated. And Descartes actually used this symbol for a line segment. You've got 2 points A and B. He said, if I just want the actual line segment connecting them, draw a bar above them. He wasn't actually saying vinculum, but he was aware that it was actually a nice coincidence that his notation to a line segment matched the notation of group those points together. It's kind of nice. The vinculum actually appears in one other spot. In an algebra class, here's the expression, 2x plus 10 divided by 2. There's something very tempting for kids to do right here, without thinking. Do you see the 2 there? See the divide by 2 there? It seems very natural just to cross out the 2's and get x plus 10. Turns out it's not right. Because it's not right, so just look, we have a vinculum there. Vinculum means a group, or that must be one group. It's not, we can't just divide part of the group, either the group gets divided or not, in which case everything gets divided by 2. So vinculum means groups, actually it's the 2x gets divided by 2 and the 10 gets divided by 2. So if we teach kids the story of the vinculum, the human story of the vinculum, it can actually help an algebra class. So this is a very common student mistake, and with no context, no story, I don't blame kids for doing it. But with the storyline involved, it can help tremendously. So I'm actually I'm on several missions in my life, and one of my missions in life is actually to bring back the vinculum. In fact, I have a teacher that's made t-shirts saying, bring back the vinculum. So we can print the vinculum with ease on a computer. I have no trouble making these slides. Bingo, just bring it back, because I think life will make much more sense for kids. Yes, if you take notes, take one thing. Bring back the vinculum. I can stop now, I should stop there as well. All right, carrying on. Let's go to my second principle of these immodest things in my head. Use common sense, work very hard to avoid hard work. That's what mathematicians do. They'll spend a lot of time thinking about how to avoid doing work. Very important task. So it really means pausing before you leap into action. And being confident, relying on your wits. And I said nudge your way again. Do you like this? Nudge your way makes sense to you? So it's not really. Okay, you grew up with the Commonwealth system. Does it make sense to you? Nudge your way
yeah, it makes sense. Yeah. We don't use it, but it did make sense.
Yeah, okay, I'm curious. All right, just think your way through things. Be confident, take patience, and rely on your wits. Follow your nose. Okay, here's a very straightforward example. What's 43 take away 27?
43 minus 47.
Sorry?
It's 43 minus 47.
43 minus 27, and what's the answer?
16.
Is it 16? I wonder how you thought about it. Did you do that in your brain? Exactly, what's that? Did you do the standard long subtraction algorithm, which is right from left, and you do 3 take away 7, you have to carry the 1, blah, 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 blah. No. I bet you did something else in your head to get 16 so quickly. I'm curious, did you do what my brain naturally did? Think 3 and 10 and 3, or something like that? No? What were you guys doing?
Yeah, similar thing. I basically took like 30 out and I had 13 and then added a 3 to it.
Okay, so you're playing with it. So here's one way you play with it. This is what they do in middle schools and primary schools now, I believe. So here's 27, 10, 10, and 7. Here's 43, all that. Well, to get from 27 to 43, you need an extra 3 to complete the 10, an extra 10, and there's still another 3 to go. So you think 3 plus 10 plus 3. Get 8. So you're playing similarly, some other version, which is all great. I certainly did not do that. In fact, it's really interesting to me. This is how we usually make change. For example, if I buy something for 73 cents and I hand $1, most people think, okay, I need 2 cents to get to 75 and another 25 cents to make the $1.
Right.
Okay? There's a very strong movement in different parts of North America to go back to the basics. And they say, we need to teach our kids the standard algorithms. They have to know them, otherwise we're really hurting them in life. And one example they come up with often is that, look how shop clerks can't make change anymore. You know, you had someone, you buy something at $1.85 and you give them $5.05, and the extra 5 cents throws them.
Yes.
Right. The funny thing is, the back to the basics, those people say we need to teach everyone this. Do we expect shop clerks to pause, get out a piece of paper, and do the Driscoll long subtraction algorithm? No. We expect them to think, okay, you gave me $5.85, need another 5 cents to get to 9, another 10 cents to get to $6, need $4 more to get to 10, and then an extra 5 cents. We actually want shop clerks to do this. Yet we're demanding we teach everyone to do that. It's a lovely contradiction there. Because we just have to think our way through what we actually want for the next generation. Anyhow, carrying on. If I was forced to do the long subtraction algorithm, someone said, no, James, you must practice long subtraction, and I was given that problem, I'd say, ick. Does that look fun to do? No. So what I would personally do is probably change it. What if I subtracted 5 over the top of the two numbers? They're still the same distance apart. In fact, right now, I can see, another 7 gets me to 170, another 30 gets me to 200, another 800, so 837. Oh, but I cheated. I didn't actually do it. I was told I had to use the long subtraction method, I just cheated. So in which case I would say, okay, I'll take one more from each to make my life really easy. 982 is 7, 986 is 3, 91 is 8, no carrying or borrowing would be called it. If someone's going to force me to do long subtraction, I'm not going to do the horrible thing, I'm going to change the something much easier because I hate hard work. Let's teach kids that sort of flexibility. Wouldn't that be amazing? By the way, I actually lied just then, because I actually would do this directly. I'd go right to left. 1 take away nothing is 1, 0 take away 1 is -1, 0 take away 6 is -6, and 5 take away 8 is -3. And I'm actually correct. Because that 1 is really 1,000. This -1 is really -100. That -6 is really -60. And that 3 is -3. Can you see the answer 837? I'm strange though. I like to play. That's pushing it, that's pushing it. I admit that's pushing it, but
That's very long-winded, though, I can see it.
yeah, yeah. So it's just if I had to do it on paper, you forced me to, I'd actually do it this way. If you were,
You have kids with that?
I do actually, I'm kind of weird. Yeah. Check out something called Exploding Dots, which is coming to the world next Tuesday. All right. Let's think about this. Let's just use common sense. What's 20 divided by 5? That means if I draw a picture of 20, I'm asking how many groups of 5 do I see? I know it's very straightforward. I think I see 4 groups of 5, so 20 divided by 5 is 4. Okay, that's straightforward. But keep that thinking in your mind. What's 605 divided by 98? Very roughly, what's the answer? Give me a ballpark answer. 6. So you thought 600 take away divided by 100.
Right.
So in that picture, in your mind, you've got 6 groups of 100. We're not looking for groups of 100, we're looking for groups of 98. So we're off by 2 every time.
So 2 times 6.
And there's an extra 5 dots floating around. So you've really got this picture in your brain. Groups of 100, and they're all off by 2, and an extra 5 floating around. So the answer is 6, with an extra 17 dots left over. 6 groups of 98, with the remainder of 17. I'm just avoiding hard work. Anyhow.
What did the R mean? 6 or 17?
Sorry?
What is the R?
Oh, in America, capital R means remainder of 17. 17 dots left yet to be divided. In Britain, they do small r, I believe. In Korea, they do ... 17.
Right.
And mathematician writes 6 plus 17 divided by 198, still waiting to be divided.
Right.
Whatever grade level you're on, you have slightly different notations. Remainder. All right. What's 15% of 62? That's hard. What's an easier problem? What's 10% of 62? 6.2. Plus, 5% is half of that. Must be 6.2 plus half of that, 3.1. That's much easier, like that. 1 kilogram is 2.2 pounds. When I came to America from Australia, I was thinking, my brain thought kilograms, and I come to a country, everyone was thinking pounds, so I had to do this a lot. So, what's 34 kilograms equivalent to in pounds? What's the easiest way to think your way through that? No hard work.
Double it, 68.
Double it, and then I'll do 0.2 of it, which I guess is basically double again, but off by a bit. 68 and 6.8? Much easier. So you're brilliant thinkers. Just common sense. We teach these principles in Algebra 2, so let me do some actual high school mathematics with you. So grade 9 or 10 is a typical place to do these things called quadratics. Solve things like x plus 2 squared equals 25. The very standard way to do it, if you're really a traditionalist, to say, okay, to solve a quadratic equation, you must expand it out, like I did with a rectangle, x plus 2 times x plus 2. It must be set to equal 0, and then you off you go and do the quadratic formula or factor, whatever you're meant to do. Nothing wrong with that way, that's fine. All correct mathematics is actually correct. That seems hard though, because here's how I would do it. I taught my kids to do it. I'm basically asking, something squared is 25. Therefore that something better be 5 or -5. So x plus 2 is 5 or x plus 2 is -5. Subtract 2 from everything, x must be 7 or 3, or -7 or 3. Much more natural. Much more natural. Avoid hard work. Work hard to avoid hard work. That's the life lesson of this one. If I really want to be cruel, x minus a times x minus b times x minus c times x minus d times x minus e times x minus f, all over x minus y times x minus z, which can't remember z. If I was to expand that out, what would the final answer be? And this is just a cruel question. What's the one that's right before this one?
X.
X minus x. What's x minus x?
0.
Whole bunch of things times 0 must equal 0. If you had the patience to expand all that out, you would get 0 in the end, but no one in their right mind would ever do that. So that's if you want to be cruel to people about teaching how to avoid hard work, there's a terrible question to give them. That's my point. All right. Here's one thing that when I talk to high school teachers, this example seems shocking to them. Often because the way it's taught at schools befuddles me. For some reason, it's important that we teach kids how to sketch graphs and formulas like that. Apparently it's important, that's fine. I don't mind doing arcane things that's done with joy and delight. That's fine, but do whatever you like with joy and delight. So if I'm going to sketch this thing, let's make it fun. I was wild, no teacher would ever let me put exponents like that on this because that's considered too hard. So here's a pretty wild one, let's just have fun. So when I've asked to graph something like this, I say, are there any interesting values for x that just come to your mind right now? Are there any x values that could be interesting to you? So just leave it to you. Give me one. 5? Heard that? If I put x equals 5 into that formula, what happens? I get 0 times the word. So I get 0. The graph is 0 at 5. Any other interesting x values?
3.
3 or negative 3?
Negative 3.
Yeah, because that would make that then 0. Yeah, negative 3 would be interesting. Negative 7 would be interesting. 2 would be interesting. That would make them all 0. So there's 4 really interesting values. I've plotted 4 points already. They all could be zeros. By the way, I think there's 2 more obvious interesting values in my head right now. Tell me about x equals 1,000,000. What sort of number comes out of this formula if I put x equals 1,000,000 in this? Huge positive times huge positive times huge positive times huge positive would be
Hugely positive.
so if I'm drawing a graph of this thing, when I go out to 1,000,000, it's way up there. Tell me one more interesting value for x. I have to stand on this side of the stage for it. Negative, it's going to be the other extreme. Put a negative in, and a huge negative number to an odd power would be negative, huge negative times huge positive times huge positive times huge negative discount, there's odd powers there, would be the net result huge and positive. So I've actually got a pretty good picture of my graph right now. It's 0 at those numbers, and it's huge and positive over there, and it's huge and positive over there. Pretty good. I admit it's missing some details. But here's the thing. We found all the places where this graph can be 0. It can't be 0 anywhere there. So it's either completely up here or completely down here. So here's the problem. How do I know if my formula is up here or down here for the values between 2 and 5? What can I do? Now, of course, I'm giving you like an 11th grade algebra class in the middle of context here. But kids will tell me, well, okay, I want to know if it's either positive or negative down there. Why don't I just try all the numbers in there? Give me a number between 2 and 5. We can just try it, see what happens. Give me one. 3, good answer. Let's put in 3. This would be what? 3 take away this negative to an odd power, so it's still negative, times 3 positive, times positive, times positive, so the whole result is negative. Bingo! So the graph is doing stuff down below here. But I can do that for each spot, figure out where it's positive or negative, and I know I've got this information. Oops. It's definitely positive on this side, it's going up. Must be, you find it's negative there, you find it's negative there, you find it's negative there. Do you have any sense of what the graph looks like now in your mind? Yeah, it must be like coming down, must be doing stuff down here, touch Oh, it's negative again, must be doing stuff down there, touch, must be doing stuff down there, touch, and you actually go through. Bingo, so you just draw any squiggle you like, it's fine. By the way, a lot of people object to me drawing things like bumps and things in here. The fact is, we don't know what it's doing down there. All we know is just under the x-axis. So anything you draw is actually legitimate. It's not until you get to calculus that you might be able to start to get some sense of shape down there as well. But in algebra class, it's the best we know, and therefore any picture goes. It's all game. Full marks for a kid drawing me that. All using common sense. That's all I want to do. I'm actually going to really push. Let's do some more high school algebra. Do you remember parabolas, these things called quadratics? This y equals x squared stuff. They're definitely symmetrical U-shaped graphs. People are obsessed with them in high school math. Every U-shaped graph you ever see is basically a parabola, quadratic. All right, so here's a really strange question. One of these parabolas passes through these points, 2, 5, 3, 6, 10, 5. Where's the vertex? So the vertex of the parabola is where's the dippy down point? Where's this little bottom bit? The thing is, you can answer this question with common sense. Because to me, when we teach parabolas to kids, and we're obsessing about teaching parabolas to kids, it's really a story of symmetry, the power of symmetry. The message is not actually out there in the curriculum books, it's all about getting answers. It's really about symmetry. If you know something symmetrical, then use that to your advantage. In fact, I've given you two symmetrical points. I've given you 2, 5 and 10, 5. We've got two symmetrical points on a symmetrical graph. 2 and 10 both give you 5. Where must the middle be, by common sense? It's 6. We've got two symmetrical points on a symmetrical graph. We've got 2, 5, 2, 6. You know then, by symmetry, the middle point must be at 6. So what that version is doing is trying to 6. Common sense, the power of symmetry. That's all the story of it is there. In which case, I had to do like a real honest 10th grade algebra question, and kids had to sketch things like this, to which I say, ugh, personally. I say, okay, we know these things are symmetrical graphs. Let's use symmetry to our advantage. We don't like hard work. Let's avoid hard work. No one likes hard work. So the question is, can I find two symmetrical points in that formula somehow? And right now it seems hard. And the only thing I can think to do is mess around with the x part, to try to rewrite it some way to find two symmetrical points on a symmetrical graph. All right? The only thing I can think to do is maybe just pull out the x's here. I'm just playing, I don't know if it's helpful or not. Now, of course, obviously I set this up so it is helpful. Suddenly I see two interesting x values. X equals 4 is interesting. So when I put in 4, I get y equals nothing plus 7. And x equals 0 is interesting. When I put x equals 0 to this formula, I get 0 times stuff plus 7. Both x equals 0 and both x equals 4 give y equals 7. Now I've got two symmetrical points on a symmetrical graph. I'm basically done. My work is done, finished. So what I've really got here is a summary. I know my graph is going to be a symmetrical U-shaped graph on these two symmetrical points. I know it must be having a line of symmetry between 0 and 4, must be 2, so it must be just some U-shaped graph that does this. Ooh, actually there's a problem. Maybe it comes down and just touches the x-axis. Maybe it comes down and goes below the x-axis, I'm not sure anymore. So one more little detail to figure out. How did I figure out whether it comes down and sweeps above, on, or below the axis? And then some fabulous student will say, well, why don't we just put in x equals 2 and find out? And you put in x equals 2, and you get 2 times negative 2. What's that, negative 4 plus 3? It must be 3, being that must be above the axis. Piece of cake. Nut your way through it, follow your nose, use common sense, use symmetry to your advantage. Grand. Wow. Are we having fun? Shall I carry on? I'll carry on. Let's go down a notch. Find a fraction lies between 1/11 and 1/12. Here's my quirky brain, 1/11 and a half. That will work. Is it correct? The funny thing is, most people object to having non-integers in fractions, so I don't know why, it's fine. It's mathematically solid. If you object to that, you can fix up the answer. What can I do to that answer to make it more socially acceptable? 11.5. In fact, people still complain to about 11.5. You could do 11.5s. Or you could just double the top and double the bottom and get 2 23rds. If society prefers that, sure, let society be happy, but that was fine. Nothing wrong with that. But I like 10.5, 11.5, that was good, because I eventually find 10 fractions between 111 and 112. You can do 111.1, 111.2, 111.3, you can find lots of them. How clever. Clever. Great. Carry on, let's engage in the art of mathematical play. This is now the joy of being a mathematician. In fact, here's what I started with, this 5 by 5 grid of dots, which we first saw today as 1 plus 2 plus 3 plus 4 plus 5 plus 4 plus 3 plus 2 plus 1. But I claim we can look at that picture a different way and see the sum 1 plus 3 plus 5 plus 7 plus 9, the sum of the first 5 odd numbers. Can you see the first 5 odd numbers in that picture? Yep, 1, 3, 5, 7, 9 is somewhere in there in a very natural way. Again, which country am I from?
Australia.
Australia. We throw boomerangs in Australia, apparently. Think of boomerang shakes. There's one dot right in the corner. Then there's 3 dots, the little L shape there, like a boomerang. And then there's 5 dots, the next boomerang.
Why is that?
And so, why is it like that? Because there it is. That's why. Yeah? The sum of the first 5 odd numbers, 1, 3, 5, 7, 9, is all 25 dots. It must be 25. Beautiful. Is that the power of a picture? Is that glorious? Okay then. What's the sum of the first 10 odd numbers going to have to be? Some of the first 5 odd numbers was 25. Some of the first 10 odd numbers would be
75
75
or 50.
or 50. Which is it?
75.
1, 3, 5, 7, 9. The first 5 odd numbers for a 5 by 5 grid. Therefore, the first 10 odd numbers for a 10 by 10 grid, which would be
100.
Would be 100. It's actually 100. What's the sum of the first 1,000 odd numbers? Must be the boomerangs of a 1,000 by 1,000 grid. Yep. Cool. In general, the sum of the first n odd numbers is n squared. So we've just discovered a formula, not part of the curriculum, shouldn't be teaching it to my kids. There it is, there's the first 10 odd numbers, 1, 3, 5, 7, 9, 11, 13, 19. Must be 10 times 10, must be 100, just like you said. But then I'm perturbed. Why this bias towards the odd numbers? What's the sum of the first 10 even numbers? The correct answer is I don't know. Can we find out somehow? Can I play with that formula and somehow get it to be the first 10 even numbers instead?
Oh, yeah.
Yeah?
1 and 4, 1 and 5, 1 and 7.
Oh. I like what you're saying. You think of this 1 and 3, this 1 and 5, this 1 and 7. I like adding ones, but I don't think I'm going to reuse this one. I'm going to do what you said. I'm going to add 1 to all of them. 1 and the 1, the 1 and the 3, a 1 and a 5, a 1 and a 7. Is that making 2, 4, 6, 8? Yep, up to 20. Now, that's what we want in life right there. But there's consequence. What's the consequence of me adding 10 ones to the left? What do we have to do? Balance it out. Add 10 ones to the right. Therefore, I think we've just discovered that some of the first 10 even numbers is 10 squared plus 10. God, we're just playing, this is fun. Except I can't help myself right now. It seems awfully tempting to divide that green line by 2. What if I divide that green line by 2? What would I get?
The green line.
Yeah, 2 divided by 2, plus 4 divided by 2, plus 6 divided by 2, all the way up to 20 divided by 2 equals 1 plus 2 plus 10 would have to be 100 plus 10 divided by 2. That's the formula we started off with today. That was what I had to teach my kids as a high school teacher. The sum of the first n numbers is n squared plus n over 2. Just coming a completely different way. Math is so connected, it keeps coming back on itself. Brilliant. Wow. In fact, if you let kids go free, and kids love to play, they can do some really astounding things. So I had some students in 2009 that actually played with what's called the Galilean ratios. Galileo discovered If you take the first odd number and the next odd number, you get 1/3. You take the first 2 odd numbers and the next 2 odd numbers, you get 4/12ths, which is 1/3. You take the first 3 odd numbers, next 3 odd numbers, you actually get some number which I can't do arithmetic, 9/27ths, which is 1/3. So you found that doing a set of odd numbers and the next set of odd numbers, the fraction's always 1/3. And those kids came up with a purely visual proof using these ideas. They actually, you see here the first 4 odd numbers, 1 plus 3 plus 5 plus 7. Then the next odd numbers, 9, 11, 13, and 15. Is it now obvious that the first 4 odd numbers are 1/3 of the rest of the picture? There you go, the fraction must be 1/3 every single time. The power of playing with the sorts of pictures we were doing with those boomerangs. In fact, they went really far. They came up with all sorts of crazy, crazy relationships beyond Galileo. All with pictures, playing with pictures. And they published this paper. Published paper by kids, just playing with the picture. Play is great. Play is fun. Let's play. People love to play. All right, gosh. There we go. Age-old question. Why is negative times negative positive? Oh, yes. Oh, yes. All right, let's do it. Let's play. So multiplication we saw today is about the areas of rectangles. So let's go wild. I'm going to allow my rectangle to have negative side lengths. Why not? Just play. And it's actually okay, because look what happens. Consider 17 times 18. It's really this picture in my mind. It's really 10 and 8, 10 and 7, because I don't like hard numbers. So I'll break the 18 into 10 and 8, and 10 and 7. And then I can fill in the pieces. 10 times 10 is 100, 10 times 8 is 80, 7 times 8 is 56, and so on. You have 100, and then 80, and then 70, and 56. The answer is 306. Now, if I let myself get quirky and allow myself to have some negative side lengths, what if I keep the 17 the same and think of the 18 as 20 and a negative 2? You might think I'm kind of strange. Look, the math is actually still consistent. 20 times 10 is 200. 10 times negative 2 will be negative 20s. 10 groups negative 2 is negative 20. 7 times 20 is 140. And 7 groups negative 2 is negative 14. And that adds up to what? 340, 320, 306. It's consistent. Or if I go the other way around, if I get quirky with the 17, 20 and negative 3 as opposed to 10 and 8, check all my numbers, I think I've done it correctly there, it is still 306. So the math wants to believe that we can play the algebra reflects the geometry and the geometry reflects the algebra. All right, so if you're starting to believe that, then let's get double quirky. Let's be weird on both numbers. And this one's good because there's 18, 20, negative 2. There's 17, 20, negative 3. And within it, it's got the mysterious question. We've all been trained to say that negative 3 times negative 2 should be positive 6. That's what we've been trained to say. The real question is, does the math want to say that? Not what I was being taught by a teacher, but does the math want to say that? Let's find out. Can we do that piece? Is that okay? Can we do that piece? Is that okay? 20 groups of negative 2, negative 40, negative 60. I'm going to be honest. There are the numbers. 400, negative 40, negative 60. 7 to 8 is these numbers plus the mystery piece. We've just done the problem 3 times in a row and got 306. The answer is only 306. In which case, what's the math telling this number has to be? Well, if you want math to be consistent, mathematics wants us to be positive 6. So for the mathematics to be consistent, mathematics is telling us, please make negative 2 times negative 3 positive 6. Now, I know I've drawn pictures, but actually the rules of arithmetic are all encoded in this geometry. So the rules of arithmetic we choose to believe that say, for this reason, for math to be consistent, we need it to be positive 6. It's kind of astounding, just from playing. I'm going to push ideas. I'm going to push it up to some advanced mathematics now. Sine and cosine, trigonometry. It's really sad to me that trigonometry is first taught as though it's about right triangles. It's not really about right triangles, it's really about circles. Because mankind had all these fundamental questions. They saw the sun rise in the east, go up over our heads, settle in the west, and another 12 hours, apparently I guess it did this or something, rise in the east, go ahead, settle in the west. So they were very aware of, they knew it wasn't circular motion, but for the first approximations, it's circular motion. And a very natural question is, when you look at the sun, mankind probably wondered, how high is the sun? This is like a very natural question. So actually Indian scholars first started really developing really serious mathematics to try to work out the height of the sun at different angles. They want to know how high is that sun. The trouble is, the only thing you can measure is the angle you're looking up. That's the only thing we can measure down here on Earth. So the question was, if I know different angles, could I work out the height of the sun at different angles? And the story of trigonometry was born. It should be called circleometry. It's really about circles. The motion of stars in a circle. To make the math tractable, they said, we don't know how far away the sun is. Let's just call it one great big astronomical unit, which astronomers actually call 1 AU, astronomical unit. So they developed all the mathematics to work out the height of the sun at different angles of elevation. And then it wasn't until the 1500s, this German fellow, Rheticus, said, no, this is too hard for school students. Let's forget about circles. Let's erase all that stuff.
What's the name of the?
Rheticus, R-H-E-T-I-C-U-S, I believe. Yes. He wrote a book about how you do the entire theory without even mentioning circles, and made it all about triangles. And that became the norm for kids. Story of Sokotoa and all that stuff. Actually, I would say teach the story first. How high is the sun? And bingo, it all makes sense. In advanced classes, you'll actually try to work out how does the height of the sun change as it goes round. And you start drawing graphs like this. Is that the sort of thing you remember from your past days? All it really is this. You've got some point going in circular motion, and you're seeing its height change. Well done, sir. The funny thing is, if I mention its height, I don't have to be able to do this for you, then I can just show you the circular motion side on, and all you're seeing is the height go up and down. Is that right? You just see that blue dot go up and down, you don't have a sense of circular motion. So if I look side on, that's what the side dot looks like to you. In fact, this is why physicists all the time like to approximate waves by sine waves, because in the universe, there's really only two types of motion, just go straight line or spin. And if you're looking at something spinning side on, all you see is that wave. So often sine waves appear in nature, because you're seeing something circular side on. Yeah. My point is, give the human story to stuff. But also, if you really want to play, why this fascination with circles? What about points? What if the sun followed a square path? In which case we have squine and cosquine. And it's actually kind of fun to work out how squine changes. The squine goes up for a while, and then the height of the star stays the same for, what's that, 45 degrees? Still height 1 at 90 degrees, still height 1 for 135 degrees, then it goes down. So you actually try to draw the squine graph if you want, just have fun. But it's a constant. The hard part is to figure out what it's doing as it goes up. Because it goes that shape. It's all squine or something. I'm just having fun. Anyway, pushing on. If you want a hard one, work out the graph of tank. Squine over cosquine. All right. Pushing on, so not too late. Let understanding prevail. Let's not memorize stuff. The distance formula. This is one that came up very early on for me as a teacher. If I want to know the distance between 2 points, I just see this picture, back to right triangles, and kids learned very early on in middle school a thing called the Pythagorean theorem, that this long side squared equals the medium side squared equals the short side squared. In which case, if I want the distance, it'll be just the distance is, I don't know, 2 sides squared square root of. I wrote diff for difference, just difference of the x values, difference of the y values, bingo. So to me, the distance formula is not a formula, get rid of that part, it's just that picture and do the obvious Pythagorean thing. Unfortunately, we teach kids to memorize things that look like that. Which is the formula is correct, don't get me wrong, is that exactly, but it's very scary. And in particular, kids muddle up pluses and minuses all the time. You've got nothing to hold on to, then there's actually nothing to hold on to. So you've got nothing to hold on to, and if you forget which is plus and minus, you're doomed. Okay, this is math. Why not? If I had to actually solve this, I can't help but notice x squared, it's all about squares again. Let's draw a square, x squared. Unfortunately, there's more to the formula. It's not just x squared, it's also a 4x and it's also a 1. So let me also add to this picture of 4x. But I like squares, so let me do pieces that are symmetrical. Let's make the 4x a 2x and a 2x. Let's keep it symmetrical. Symmetry is our friend. Okay, now I want that to be 2x. Something times x makes 2x. This number at the top better be 2. Which means that's 2. I've got no choice to make that 2 times 2, which is 4, which is annoying. Because right now I've got an x squared, I've got a 4x and a 4. But I want a 1. That's very annoying. So I give up, I leave. Or we can push on and say, well, if you want to be a 4, make it happen. Add 3 to everything. So I'm going to have x squared plus 4. There it is, that picture is 89. What's that picture really? Oh, it's this whole square. So kind of do it backwards. Something squared is 89. Back to how I want to solve quadratics. Something squared is 89, common sense. All right. Here's a hard one. In other pre-calculus, kids ask things like, what's the inverse of sine of 1/2? That is, where does the star have a height of 1/2? If I say it's actually the height of the sun is 1/2, it's actually a much easier question. I draw my picture. I want my sun to be either half a unit up over here or it could be half a unit up over there. And the question is asking what angle makes the star half a unit high. Now kids have to memorize all sorts of things about, root 3s over 2s and 1 over root 2s and all sorts of weird stuff. But actually, can we just figure our way out? I can't help but notice, look at this triangle, it's 1.5 at the side of a half. That triangle is very compelling to me. It's half of one of those triangles. Am I right? So it's side length 1, side length 1, side length 1. I was thinking of a triangle from my geometry class where the angle is equal to a triangle. 60 degrees.
Right.
And the angle I want must be half of 60 degrees, 30 degrees. So my star has height 1/2 at 30 degrees, or all the way over here to that position, which would be, 180, take away 30 degrees, 50. I mean, you will memorize those formulas after a while while sticking your head, that's fine, but you don't actually have to know them in your head. You can nudge your way through it. All right. Walk into hazy thinking. I think this is one of the most powerful principles of just clever thinking. Be very clear what you don't know. It's okay not to know stuff. It's really okay not to know stuff. One really needs to struggle and flail with ideas to truly come to internalize them and understand them. But you really need to understand why something doesn't work first, to understand why something actually does work. That's really powerful. So let me just point out, we have grade schoolers, primary school kids, are meant to be masters of the number 0, but 0 is actually very hard. And we don't let people struggle with number 0. For example, is 0 even or odd? That's a tough question. Is negative 0 the same as positive 0? Like, really, do we understand that? Is 0 even a counting number? I mean, what does 0 count? If I said to you, there are 0 giraffes in this room right now, is that because you noticed a lack of giraffes, or because you actually counted to the number 0? Is 0 really counting something or not counting something? That's an age-old question. The other one is, why can't we divide by 0? These are tough questions. But let me go through this one, why we can't divide by 0. We saw today that 20 divided by 5 is 4. And we just check that with arithmetic because I can see 4 times 5, yep, that's going to be 20. 4 groups of 5 really is 20. So I can do an arithmetic check on that one. So what's wrong with dividing by 0? Why can't I do 5 divided by 0? In fact, I believe it's 2. 5 divided by 0 is 2. There it is. I've written on the board. It must be true.
No.
Does it pass my arithmetic check? No. 2 times 0, I'm afraid, is not 5, so I failed. In fact, what number should I have written there? 2.5. Bingo. Because 2.5 times 0 equals 5. Okay, what other number should I put there? 0. All right, because 0 times 0 equals 5. Is there any number I can put there? 0 again? Because 0 times 0 equals 5. There's no number you can put there. Dividing by 0 is problematic because there's no piece of arithmetic that's consistent with dividing by 0. Whatever number you try to put in, you see it fails the check. Except in this case. 0 divided by 0 is 17. And I am correct. Because 17 times 0 does indeed equal 0.
No.
Yeah? Passes my check. Whoa. Whoa. This one suffers from a different problem. this any number you want to put in there will work.
Yeah.
So the trouble with this one is that no number works. The trouble with this one is that every number works. So people say, dividing by 0 is just dangerous, don't even go there, just don't even bother doing it. It's just, arithmetic just goes haywire. All right. So let me just end off with one more example. I'll stop here because this is a long day. You know, the fact is I really don't understand exponents. For example, we said that 2 cubed is 2 multiplied by itself 3 times. 2 times 2 times 2, that makes 8. Or 2 to the 5th power is 2 multiplied by itself 5 times. 2 times 2 times 2 times 2 times 2, that makes it a 32. In which case, what's 2 to the 1th power? Multiply 2 by itself 1 time. Does that make sense? Actually, what I just said. It gets worse. What's 2 to the 0th power? Multiply 2 by itself 0 times. Multiply 2 by itself negative 1 times. Multiply 2 by itself half a time. So, what I love about how much the school curriculum is built up is that they often teach kids beautiful models to make sense of math. The models also have a beautiful next lesson. You know, here's paper folding. Often I can make sense of exponents by folding a piece of paper. If I fold a piece of paper in half once, how many layers do I have? 2 layers. If I fold my piece of paper in half a second time, 4 layers. 3 folds makes, I can't do it, 8 layers. Oh, in fact, 3 folds makes 8 layers. Every time you do a fold, you multiply by 2, is that right? 2, 4, 8. 2 to the 3, 8 layers. 2 squared, 1, 2, it's 4 layers. All right? Then if I use this model, this seems like a really good model for exponents. What would 2 to the 1th be? 1 fold makes 2 layers. 2 to the 1 is 2, according to this model. Sounding good. Is that what we taught in school? Yeah? What about 2 to the 0? Can I make sense of 2 to the 0 in this model? What if I take a strip of paper and fold it in half no times? Oh, don't even fold it in half. How many layers do I have?
0. Well, you have 1 layer.
I have 1 layer. School books say 2 to the 0 is 1. And they often say something like this, because you get 1 layer in this paper folding model. All right, let's get crazy. Can we push this model to make sense of 2 to the negative 1? Take this strip of paper and fold it in half negative 1 times. I've never seen textbooks do this now. This is my brain. Do an anti-fold, do the opposite of a fold on the strip of paper. What would be the opposite of a fold on this strip of paper?
Cutting.
Sorry?
Cutting it.
I could rip it in half this way, or I want to say it's like technically the exact opposite of doing that. What would be the opposite of folding? It's like cutting, but cut in a very clever way. What's the anti-folding?
Go inside.
Yeah, so actually there's a fold. To unfold it, what do? I do that. So I start there, to unfold that, what do I have to do? It is cutting, like peel it apart. Like imagine this like a peeled paper, just peel it apart. Actually, how thick would it be if I peeled it apart?
Turn it underneath.
And well, not even turn out, just peel it apart. Before we turn underneath, it would be, how thick would it be? How many layers is that? Half a layer, wouldn't it?
Yes.
Wow. 1 fold is 2 layers. 0 folds is 1 layer, and negative 1 folds, 1 anti-fold, peel it apart and make half a layer. School books do say you'll get 2 to the negative 1 is a half. This model is brilliant for exponents. What books often don't do is they say that models are great. They can help inspire, they can help teach you some good mathematics. But often models will eventually break down. 2 to the 1 half. What's half a fold? That's 1 fold. Do that half a time instead.
You still get 2 folds. You still,
Well, what's half a fold? Yeah, first of all,
like half of that.
that? Is that half a fold?
Yeah.
I don't know. The fact is, I don't know. You don't know, I don't know. I have no idea what half a fold means. So the point is, this model breaks down. It's to go away. It can inspire, it can lead to things we want to believe about exponents, but at some point you've got to let the mathematics speak for itself. So the real question right now is, what's the mathematics we want to believe about exponents? and like negative times negative equals positive came from the mathematics. Mathematics will tell us what to do with things like this. It has to be a story of the mathematics. So this is my point. I, as a mathematician, know nothing. I really can't tell you anything about this world. All we do in mathematics is figure out if you choose to believe this, this, and this, then here are the consequences that follow. No one says in the first place you have to believe these things. That's up to you. And the engineers and so forth. Mathematics seems to work very well in the practical world, but as a mathematician, I'll help you figure out what things we want to choose to believe and what some of the consequences will be. You know, life is like this. I don't know how to be a parent for the first time. Yes, there's lots of things out there that I'm meant to be and do, but I have to flail and figure it out for myself on my own. And in the end, you have to just try, nudge your way out, follow your nose, follow your common instincts, try to do the right thing. So, in the end, I don't know how much this is important for our next generation to learn the actual mechanics of mathematics, but I do think the thinking behind it is actually important. So, you know, I talk about the power of a picture. I talk about using common sense, avoiding hard work. I talk about letting play be a way to go. I talk about walking into hazy thinking. Find the areas that are hazy and try to think your way through them, nudge your way through them. That to me would be a great gift for the next generation. If our next generation can say, do you know what, I really actually don't understand that. Let me probe it deeper for myself, rather than just walk away saying, oh, that doesn't make sense to me, let me move on. Let's have to teach our next generation the confidence to actually walk into hazy thinking in all aspects of life. And I think actually mathematics is a great way to help build the confidence to do that. So that's why I absolutely loved being a high school math teacher. Not because I cared about dividing polynomials, not because I cared about the quadratic equation, but I cared about the thinking and the story behind all that material. It was the vehicle for teaching good math skills. So I'm going to stop there. Thank you.
Do you demonstrate in your class there's a layer in order to comprehend, to make it more simple to comprehend? If you don't have anything to demonstrate with, so how would people know? The students?
Right, so then the real question becomes, I wish I had a board here. I mean, this seems very compelling. This is actually beautiful. I actually like this model. And I also love the fact that it breaks down. So now brings the question, what do we really like to believe about how exponents work? And it turns out, what we tend to get to in discussion is, okay, if I did 2 cubed times 2 to the 5th power, so I get 2 times 2 times 2 times 2 times 2 times 2 times 2, I get 2 to the 8th, is that right? 8 2s? So we like to believe that 2 cubed times 2 to the 5th equals 2 to the 8th. With me so far? Like, I wish I had a board, I don't have a board, I wish I could write it. So 2 cubed times 2 to the 5th would equal 8 2, so it's 2 to the 8th. 2 to the 3 times 2 to the 5 is 2 to the 3 plus 5. 2 to the 7 times 2 to the 100 would be 2 to the 7 plus 100. We realize that that multiplicative property is what we really base exponents work. So as soon as we say that, then the question is, okay, we like to believe it works for whole numbers, it fits with the mathematics, it fits with the paper folding, it gets near to other numbers. So then the question is, what would be the logical consequence of what we like to believe if we let it work for all numbers? And then you'll discover that that rule wants you to say 2 to the 0 is 1. It wants you to say 2 to the negative 1 is a half. And it wants you to say 2 to the half is the square root of 2. The mathematics then tells you what it wants it to be. So I use the breakdown of a model like this as a way to get to the discussion, what do we think is the important piece of mathematics that this is telling us that we should hold on to all numbers? In which case, what are the logical consequences? And it's a high school topic. Now for middle school, it's a different story because they need to get used to exponents first. So I can just stay with the integer exponents and we're good. But the next level of conversation is, okay, how can we push these ideas further to more numbers? What does the math want to tell us is going on? Does that help? Is that making some sense? Okay, great. All right, so how are we with the salute? Do you want me to actually, you've got it? Should we end off the evening with one final math salute? All right, just to celebrate mathematics, one time, the math salute. Arms out front. Oh, you missed this early on. Right hand over left hand. I'm watching everyone this time. Palm to palm. Wiggle the little fingers. Wiggle the thumbs. Wiggle the little fingers again. And when you're ready, come on.